All right, everybody. This video is kind of running through how to actually do something with a sample data set. In this case, we're going to do regression. So a couple videos I've been posting about how to load in sample data sets, which are incredibly useful for kind of learning tools, I think. I think they're phenomenally useful, but I didn't really show you how to do anything with them. So what I'm going to do here is actually walk you through basic regression and hopefully get you familiar with how to work with these data sets and give you an idea of how regression works as well. So with MATLAB, I'm going to walk line by line here, so item by item, and hopefully by the end you understand each of these steps. The first code here, the first line is line 2. I have clear all, close all, and CLC. Clear all clears my workspace, which is over here. If I have any variables, it gets rid of them. So that way I don't have any competing variables that might be brought in. And it clears my memory as well, which is great. I close all, so if I have any figures open, it closes them. And then CLC stands for, I believe, clear command window, which is this here. If I have any code written, it will actually clear that. So if I run that real quick, press F9, you don't really see anything happen, but if I had variables up, it would be clear now. Next, you'll load in the data set. So here, we just have load Fisher Iris. And you don't have to save it to a variable because it actually has its own. So you see mesh and species. Species here is actually the the species of flower that each row is. So the first 50 are Setosa, the second 50 are versicolor, and the last 50 are virginica. That means we have 150 measurements, 3 different types of species. The measurements here, this actually is more like variables. These are the variables that are collected or recorded for each of these species or each of these data points. So what I don't like is there's no names. It's a matrix, and it's a little frustrating to work with because you don't necessarily know what these are. What's nice about this Iris dataset is you can find it anywhere. If you Google the Iris dataset, Fisher Iris, whatever, it'll come up. If you go to Kaggle, as I did, I just went to the Kaggle data competition website, you'll see this is actually the formatting of the data set. So ID we actually don't have. It's already kind of pre-listed here on the side. But the first column should be sepal length, then sepal width, then petal length and petal width. I feel fairly confident in saying that that is probably correct because this is sepal length, which is a larger number than sepal width. This is petal length, which is a larger number than petal width. So that seems to make sense to me. And then species would be this 5th column, but we actually don't. It has its own variable, so it's not there. Next, I do like working with tables. One of the reasons is because it has variable names or column names. So I'm going to actually create a table, and I'm going to put all this into a table to make it a little bit easier on myself. So I created an empty table. You'll see it here. It's a 0 by 0 table. And then I'm going to fill it with variables. Once you have a table, in order to create columns, you can actually just do this dot notation. So var table dot, and then I have the name of what I want to call it. And I'm going to make it equal to the first column of this mes variable. And then I move down and it's sepal width, and I make it the 2nd column, then the 3rd column, then the 4th column. Finally, I'm going to create a species column. So that wasn't present in the original, or at least this original here, but I want it to be on part of the same table. Excuse me. The thing I want to point out, though, is depending on what sort of algorithm you're running, there's a chance that it may not like having a name as the output or a categorical variable as the output. So, well, it will be categorical, but you have to trick it a little bit. So it doesn't want a name as the output. If that's the case, you may need to convert the Setosa, virginica, versicolor into numbers. So group 1, group 2, group 3. In that case, MATLAB has this great function called group 2 index, and then you just put the column that you want. So in our case, the variable that you want is species. And all it's going to do is say the first type I come to, which is Setosa, is going to be group 1. Second type is versicolor, going to be group 2. Third type is virginica, it's going to be group 3, and that's it. You normally would have to do a very annoying for loop and figure out any problems that you bump into along the way, kind of swap over different cases and everything. This is just a super quick function to do that, and it does it exactly as at least I want it. So let's go ahead and fill in the variables of our table. There we go. And let's actually look at it. So now we have sepal length, sepal width, petal length, petal width, species. Great. Okay, everything's looking good. So now I actually want to do some regression. And MATLAB has two forms of regression, or two functions at least that do regression that were readily available. I'm sure there's more. One is called regress, and one is called FitLM, which stands for Fit Linear Model. Regress was kind of clunky to work with, and admittedly I struggled learning it. So I moved into FitLM. So no real reason why I'm using this one over the other than I understand it better. And it gave me what the information I wanted. So there's two ways to call this, and this I'm going to show you option 1 and option 2. Option 1 is kind of more familiar and it's kind of more intuitive. Option 2, if you get used to it, is probably better. So I'll show you the first one because it makes sense. Second one, just introduce you to how you can call it in a different way. So when you call it, it's just asking, okay, I want to fit what variable to what variable. So this is basically my x, this is my y. So it's the sepal length to the petal length. And again, I'm calling it with that dot notation. So I'm just calling that column of the variable table. So let me go ahead and run that. And also worth mentioning, I'm not detecting the species because I'm doing regression. I want to do a continuous variable to a continuous variable rather than a continuous variable to a category. There is a way to do that, I believe, and I'm going to try to figure out how MATLAB allows that. I think it's called just regression classification. I think you create thresholds or something like that. But I'm less familiar with that. We're going to do it this way just to show you how you can do it, and then we'll do some videos in the future to see if I can figure out how to do the rest. So we created our linear model here, and now I can call LM1, and when I run it, I get this awesome info. So LM1, I get the linear regression model, just a line. So Y1 just means there is a y-intercept plus x1. That's all it is. And here is where we're actually going to get the info for the this 1 and x1. So the y-intercept is negative 7.1, and then x1, which is kind of the slope, is 1.85. If I had multiple variables, and I'm going to show you that next, you would actually not just have x1, but you'd have x2. Then you get more x3, x4, x5. The reason I'm starting with 1 is because you can visualize it very easily. With regression, in particular for myself, when people were talking about it, when I saw the values printed out and everything, it didn't quite click for me until you see a plot of it. And then all of a sudden it's incredibly simple. So what I'm going to do is actually do a plot for this first step, this option 1 and option 2, and then we're going to add in a couple of variables and we're going to do a plot again on that. In this case, we have one predictor and one target, the predictor being sepal length and the target being petal length. Or if you want to call it independent variable. The next one after option 2, we're actually going to do 2 predictors. And so in our current case, it's 2-dimensional. In the next case, it'll be 3-dimensional. I stop there because once you surpass 3 dimensions, it starts getting tricky. You can start with 2 dimensions being x and y, and we'll plot it. Then you can move to 3 dimensions, and you have x, y, and z as far as a graph goes, and you can plot it. When you get beyond that, you can start throwing in things like color and shape, but it starts getting really messy, and then as you grow it, it just gets impossible. So let's continue. So we made our model. We have our estimates. Great. Our p-values are incredibly low. Everything's looking good. So now I actually want to plot it. So I'm going to create a figure. I'm going to use the scatter plot, and I'm just going to do my x and my y. And then I'm going to put some labels on it. X label is sepal length. Y level is petal length, and I'm going to put this hold on. Hold on just means that when I print it, don't let anything else that prints print on the same thing. So I'm going to come down. I'm actually going to plot a line on top of it. I don't want to overwrite my scatter plot. I don't want to just see the scatter plot and then clear it and then put a line. I want to see the scatter plot and the line together. So hold on allows me to do that. So first things first, let me plot it. Press F9. There we go. Sepal length is on the x, petal length is on the y, and you can see there's a very positive correlation from left to right. Great. Okay, so far so good. So let me go next, and this is where it gets a little bit tricky to look at, but the idea is pretty simple. So I have this increment section, and increment just means we're going to use it in the next step, and it means how many, what's the size of the steps I'm going to make in this next thing. So I have to create my x data set here, and my x data set is basically my sepal length. But the problem with that is if you just use sepal length, it'll be 150. It'll be 1 to 150 on the x-axis. And the problem is with the y output, you're not actually comparing 1 to 150. You have values of your sepal length. So you actually have to make the sepal length values the appropriate points here. So what I'm going to do is take the minimum value, that's where I'm going to start, of sepal length. I'm going to increment it by this here. And the increment is just the range of the sepal length. It's the max minus the min, and I divide it by 150. And I picked 150 because that's how many data points I have. So hopefully that makes sense. It actually took me a little while to figure out how to do this properly, but it's a very easy idea. I just want to increment by a very small amount to make sure that I get 150 points, but that they're within the range that I need. And then I'm going to end at the maximum value of that. So let me go ahead and run that. And I think I don't have increment up yet, so let me go ahead and run that. And there we go. So the increment's going to be 0.024, and the x is going to be printed. Okay, so if I were to just, let me see, I don't want to plot x. Let me just open it. Here we go. So we have our data points here. So you can see it's barely going up. Starts at 4, and then the maximum value is 7.9, which actually is the maximum value of the sepal length. So we're good. The next thing I want to do is actually the output, or the y value, needs to be my formula. The formula that my model gave me, which was y1 plus x1. So what I do here is come in, I go to my linear model 1, and there's a thing called coefficients. Let's see, where are we? Dot coefficients, there we are, 2x4 table. And within that, that's the table that printed out here. And I need to go out my linear model, dot coefficients dot estimate, because this is the column for estimate, and I'm going to take the first value, so estimate 1. That's my y-intercept. So for a normal line formula, you would have y equals mx plus b, where b is the intercept. For a statistical regression, same idea, but you swap places and it becomes y equals b plus mx. And they replace some names for m and all that, but that's basically what you've done. You put the y-intercept first now. So I'm going to do that. So I pull that value. It's going to be negative 7.1. And then I'm going to add the estimate number 2, which is the slope, and I'm going to multiply it by my x. So this is my input value. I'm multiplying that by some slope, and then I'm going to have a y coefficient, a y-intercept as well. So let me go ahead and run that. There we go, and I can plot it. And now, because I had the hold on set up on my figure, I get this lovely line here. So what I have is sepal length, and you notice it goes from 4 to 7.9, which is what we had on this x value here, what we made with this minimum with increments of a certain value to the maximum. I have my plot of all my points, and then I create a line, and it's a best fit line over that. And that was created as a best fit line due to the fit LM model. So all that's ready in there. You can always go to tools here, I believe it is. You go to basic fitting. You can go to linear, and you can actually do the same process we did for our line. The problem I have with that is that's great when you have simple data sets, but once you need to do something yourself, it may be well worth your time to plot it and figure out how to draw it yourself. And this step really is kind of the idea behind what this is telling you. So I do like that. Okay, so let's see here. I can go ahead and close my variables. I'm going to show you how to do this, the exact same process, but using a different input here. So I call it LM2, so linear model 2. Same function call, fit LM. And the other way to call this is, instead of saying, okay, here's my X and here's my Y, or my predictor and my target, I'm going to say, what is my table and what is my formula? So this is saying I want to pull values from variable table, which is right there, and my formula is going to be y equals x. So instead of saying x equals y, you start with your target, and then it's going to say is predicted by, this. And the reason this is good is because this allows you to actually add in multiple variables much smoother, in my opinion, and it allows you to add in a more complex model than the other option above would have allowed. So the option above is very intuitive and it's quick and it's easy, but once you start adding some difficulty, I think this is very useful. So let me go ahead and pull that. There we go. Now we have LM2, and just for sake, we're going to go LM2, and there you go. And if you notice, we actually have, so now your linear regression model, it actually has the values in it. So now you can say petal length, which is your y, equals, this is y-intercept, remember, 1 just meaning it's there. You also have the option to remove it. And then you have plus sepal length. And the sepal length is the x, right? And you're going to actually do that's going to be kind of the weight on sepal length. Then you have the values and you have everything you need there. So again, we want to plot it. So we're going to create a figure. We're going to do a scatter plot. And then again, here's my x, here's my y. I'm going to label it as sepal length and petal length, and I'm going to have hold be on, and that'll allow me to draw the line on top of it. So again, there's that graph, and it should look fairly familiar. Next, I'm going to do the same incrementation I did before, which is the range divided by 150 of my predictor. So I run that. Then I'm going to create all of my data points within that range. There we go. And then I'm going to input those data points within that range into my formula. And again, I'm going to have LM2 dot coefficients. If I go to it, you go to dot coefficients right there. You go to dot estimate, which is this column, and we're going to pull the intercept, which is the first row. Then I'm going to say plus LM2 coefficients estimate, and I'm going to do that, which is the slope, and I'll multiply it by my x. So let's see how we do. There we go. And now I can plot it again. Boom. And there we are. So same exact output, slightly different process. Really only this section here. But again, I think I prefer that for the sake that when you get more complex, it's very useful. Okay, so now we're going to do something a little bit trickier. So let me go ahead and close this. So now we're going to add in another variable. I'm not doing 4 variables for the reason that I won't be able to graph it. Or at least I won't be able to graph it easily or intuitively when you see it. But what we're going to do is predict petal length based on sepal length and sepal width. And I chose those more or less at random, but you could do it for a number of variables as well. So I'm using the second option's format. So I'm pulling from variable table, and petal length is predicted by sepal length plus sepal width. So I'm adding those both in. So let me go ahead and run that, and there's my LM3. We're ready. And what I'm going to do here is now plot my data, and the data now is x, y, and z dimensions. So now I all of a sudden have 3 dimensions. So same way you would do the scatter plot above, but instead of saying scatter, you say scatter 3, which is for 3D. I have my x, I have my y, and I have my z. So x is sepal length, y is I have my, it should be sepal width, and then finally is petal length. And I had a couple typos there. Okay, so let me go ahead and run this. There we go. And now what's pretty handy about this, I can click this 3D cube thing, and you can actually see your data in 3D. And you'll see petal length is on this, say, it looks like the y, but in our case it's z. Sepal length is here and sepal width is here. And it's really handy because you can start seeing relationships based on these 3 variables. Okay, so hold on, I'm not going to close that. I'm going to do the same thing here, but instead of having 1 increment, I actually have 2, one for sepal length and one for sepal width. So I actually have to specify those differently. And again, it's going to be the range divided by 150, the range divided by 150. So let me go ahead and call that. And again, it's divided by 150 because I had 150 data points and I wanted to maintain that. Then you have, I'm going to create my x, which is just going to be incremental data points between that range, 150 data points. The y is going to be the same one, so I'm going to call both of those together. There we go. And I actually get 151 data points, but that shouldn't be too much of a problem as long as these maintain what I equal. And then z, now z is my formula. So in this case, I have my y intercept, my first slope multiplied by my first values, plus my second slope multiplied by that second values. And again, if we went to, let's see, LM3, go to coefficients, whoop, not that one, go to coefficients, and you have the intercept, the first slope, and then the second slope. So here's where you're actually going to pull those. And again, it's LM3, which is what I have open, dot coefficients, which is what we just opened, dot estimate, which is the column, and then 1, 2, and 3 for the row values. Okay, so let's go ahead and run that, and hopefully we don't get an error. All right, we're good. And now I'm going to go ahead and plot that. So there we go. And here we go. So now what's really cool about this is you can actually see the relationships here. So you can start to see this is kind of the mid-range of it. You know, it's shooting right through the diagonal. It doesn't, you know, there it doesn't really look like it's fitting anything, but when you rotate it, you can see it's almost fit perfectly at certain angles. And it's fitting this data. It's basically if I had a sepal width of this value, I had a sepal length of this value, what would be the expected petal length of that? And that's what where kind of the prediction aspect comes in. If you have these two inputs, what would be the expected output? And the expected output falls in that line. And you can see it's not perfect. You know, here we have data points way out here. But depending on the information provided, you can get a very, very good estimate of what that is. So that's where regression comes into play, is kind of, you know, given these inputs, what is my potential output? Or given this output, you know, what is the impact of certain inputs? Or you know, you can play with it kind of in either direction on that. So hopefully that gives you some insight on what you can do with the sample data sets. In this case, we learned a little bit about regression and plotting regressions. And also a little bit about regression. What is regression, and what it means when you add variables. You're just adding dimensions to this plot, essentially. And again, it gets very tricky above 3 dimensions, but there are data sets that have millions of dimensions. So it gets kind of overwhelming if you were to plot the regression aspect of it. But the idea is still the same. You're looking at kind of these weights depending on the variable, and it impacts the slope of this line in this case. It doesn't have to be a line every time. It could be a bent line, it could be a it could be a shape, it could be a lot of different things. But in this case, we're working on a line. Anyway, I hope that was helpful. If you do have questions, please feel free to contact me. If you have any requests, please let me know. I'm looking for more and more things to learn and describe at very good learning levels. If I can help in any way, just please send me an email and I'll see what I can do. Thank you.